In this video, we're going to see Ebers Moll model of a BJT. So to start with, let me take the PNP BJT that we have been seeing all along the course. Now the question is, can we model this PNP transistor in a simple model so that it represents this BJT in terms of large signal model? If you observe here, we have a emitter junction in between emitter and base, which is a PN junction. So we can say this is a PN junction. So let me draw a PN junction here, saying this is similar to the PN junction that we have here near the emitter, which is emitter junction. And we have another PN junction, which is here that we called as collector junction between the collector and the base. So let me represent that also. That is a PN junction we have here. So we can say this is emitter terminal, this is collector terminal, and the one in the middle, the base terminal. Now let me call this diode as the emitter diode just for our reference, and this is the collector diode. If we take two diodes and try to connect in this fashion, obviously they wouldn't be working as a BJT that we have on the left side, because this first diode DE cannot control what happens in DC, the collector diode. And the same thing happens here, that DC cannot control what happens in DE if you have two diodes connected in this fashion. Whereas in BJT, the two junctions are interacting junctions, because the current flowing in collector junction is controlled by the current flowing through the emitter junction in active mode. So hence we cannot simply say in this model cannot represent a BJT completely. These two diodes here are non-interacting diodes, whereas in a BJT the junctions are interacting junctions. So how do we represent that here? The current that is flowing through this junction, let's say the emitter junction, is IF. We'll see why it is called IF. Now because of this current flowing through this emitter junction in the BJT, there would be current flowing through the collector junction, which is dependent on this current, let's say, which is IF. Now we have some current that flows through collector junction called alpha F times IF. So let's represent that as a current dependent current source here. That is alpha F times IF. Now our intention is not to just model the BJT in active region of operation. So let's say we have inverse active region of operation, where the collector junction is forward biased and the emitter junction is reverse biased. In which case, the current that is flowing through the collector junction, let's call this as IR, because R represents the reverse active mode of operation current flow, and F here represents the forward active mode of operation current flow through the emitter junction. Now because there is IR flowing through this, there would be current flowing through the emitter junction which would depend on this IR. That we can represent with a current dependent current source. Let me represent that here. This is alpha R times IR. Now let's call the voltages across these diodes as VEB and across this diode as VCB. Now we have seen that this model would work for forward active and reverse active, and we would go forward and even find out that this model would be valid for even saturation and cutoff. But let me mark the currents here. This is the emitter current, this is the collector current, and this is the base current. Now the model that we have here is called Ebers Moll model. We started with two PN junction diodes which are non-interacting, but in case of a BJT they would be interacting. To show that, we have shown here the current dependent current sources with alpha F and alpha R parameters in terms of IF and IR respectively for forward active and reverse active modes of operation. Now the diodes that we are showing here are assumed to be ideal diodes which have ideal diode current equations. Now having said that, let's write the equations for emitter current, collector current and base current. Starting with emitter current, IE is equal to IF minus alpha R times IR, which can be written equal to Of course, IF is the diode current equation of this diode, which is IE naught times e power VEB over VT minus 1 minus alpha R times IR. IR is nothing but the diode current equation of the second diode, which is DC. So that is IC naught times e power VCB over VT minus 1. Now coming to collector current, IC is equal to alpha F IF minus IR. We can write this equal to alpha F times IF is IE naught times e power VEB over VT minus 1 minus IR is IC naught times e power VCB over VT minus 1. Now coming to IB, IB is equal to IF plus IR minus alpha F IF minus alpha R IR. So if we segregate this, we get IF minus alpha R IR minus alpha F IF minus IR, which is equal to IE minus IC. As I mentioned, this is a large signal model. Let me put this down here. In fact, it is valid in all modes of operations. Now, IE naught here is the leakage current through the emitter junction, and IC naught is the leakage current through the collector junction. Now, to understand what these terms are equal to in terms of the device parameters, let's try to find out what is IE and IC in active region of operation, because we have derived these very equations in the previous video. So let's correlate with them and find what these quantities are. In active mode, JE is forward biased, where VEB is positive, and JC is reverse biased, which means VCB is negative. So taking this, let me write the expressions for IE and IC here. IE is equal to IE naught times e power VEB over VT minus 1. And coming to the second term, alpha R IC naught times this e power VCB over VT minus 1. As this diode will be in reverse bias, we would have the reverse saturation current, which is negative. So negative of negative positive. So we get plus alpha R IC naught. Now let's find the equation for IC. IC is equal to alpha F IE naught times power VEB over VT minus 1. Now we would get plus IC naught, because the collector junction is reverse biased, hence we will have reverse saturation current there. Negative of negative positive, hence we got plus IC naught. Now let's get the similar equations from the previous video where we derived. The equations are, now looking at this, we can say that alpha R IC naught should be equal to AQ dP Pn naught over W. And the second thing is alpha F IE naught should be equal to AQ dP Pn naught over W. And of course, if we observe here, alpha R IC naught is equal to alpha F IE naught, because both are equal to same quantity. So let me write this down here. That is alpha F IE naught is equal to alpha R IC naught. Now as these two quantities are equal, so let's call this quantity over here as IS, which means we can represent IE naught is equal to IS over alpha F and IC naught as IS over alpha R. Now having known these expressions, now let's rewrite the equations that we had. Those are the initial equations we had here, that is number 1 and number 2, which are valid in all regions of operation. In fact, to find out the relationship, we just took active mode of operation because we had the equations derived from previous video. Hence, we use them here to find the relationships. So let me rewrite those equations here. Now, if we observe these equations, we have Is as a parameter that we need to know to find these equations. And of course, alpha F and alpha R. Apart from that, it's all about the applied potentials at emitter base junction and collector base junction, VEB and VCB respectively. So the number of parameters that are present in these equations are in fact very less. Now we can rewrite these expressions in terms of beta F and beta R, where alpha F is related to beta F by beta F over 1 plus beta F, and alpha R is related to beta R over 1 plus beta R. Now I'm going to write expressions for IE, IC and IB in terms of beta F and beta R instead of alpha F and alpha R. So the equations would be these equations are in terms of Is, alpha F, alpha R and the potentials across the junctions. Whereas these equations are in terms of Is, beta F, beta R and the potentials across the junctions.